All right, request to help out with exercise 8.2. So this is constructing a TXY phase diagram using Rayo's law. And so remember the challenge here is that we'll create this vector. So by TXY, pressure is known and constant. Then we're going to create a vector of x values. We'll loop over that vector of x values. And for each case of x with that known p, we'll solve for t and y. So now the challenge here is in our equilibrium expressions, our Rayo's law expressions, we have P1 sat and P2 sat. P1 sat and P2 sat are a function of t. So within our air function, when you solve for t, you'll need to call your Antoine equation to solve for your vapor pressures using each of those guesses of t. So let's take a look at the code you sent me and see what we have here. Okay, so let's have a script. Format short. So pressure is 101.33 kilopascals. Convert to pascals. That's fine. So it looks like my vector of Antoine constants. That's fine. Looks like you have a character that won't show up on my computer. Vector of x1 values, so we're looking at a lot of x1 values. That's cool. A vector of t's and y's to collect the values that I'm going to solve for. And we have initial guess of temperature for the F0 calculations. Okay. Now let's looping to solve for t and y1. All right, so let's make this bigger as we try and figure out what we have going on here. So I'm going to loop over my x values. And try and create an air function to solve for t. And then once you have t, your goal is to solve for y. All right. So my system of equations is y1p is equal to x1 p1 sat plus x2, or y1p is equal to x1 p1 sat, and y2p is equal to x2 p2 sat. So if I add them together, I get the p is equal to x1 p1 sat plus x2 p2 sat. Okay, so I know p on the right hand side of that expression, p1 sat and p2 sat are essentially just functions of t, which I don't know. Okay, so yeah, we could first solve for t. What I would be questioning is if then we're just getting something goofed up here, trying to put everything on one line. Okay, so let me just, and then let's see. So in the new version of MATLAB, you should be able to have a script, because you have a script here, and have a helper function in it. But let me do this. Okay, I'm going to convert this to a function. We'll just call it res is. This is called McCabe. Just make it a function with no inputs. Okay. So in the newest version of MATLAB, you should be able to add helper functions to a script, but I'm just going to go ahead and rename it or recast it as a function with no inputs. So I'm going to create a helper function here. So let's do function res is, we'll call this rail to air. Okay. And for now, I'll just leave it as no inputs. Okay, we'll fix that up in a second though. Just because, again, my thought process is, so, without pulling a tablet out, is my system of equations, my system of Rayo's law equations I'm trying to solve is y1p is equal to x1 times p1 sat, and y2 times p is equal to x2 times p2 sat. Okay, so the idea would be if I add these two equations together, okay, I'd have y1p plus y2p. P's constant, factor it out. Y1 plus y2 is just 1, right? So I just have p. Okay, so adding together, I would get that p is equal to x1 times p1 sat plus x2 times p2 sat. Okay, and then I could readily recast this as an error function as p minus x1 p1 sat minus x2 p2 sat is equal to 0. Okay, so y doesn't appear in here, right? My unknowns are y and t. T, appears within my expressions for p1 sat and p2 sat, which are only functions of t. Okay, cool. Okay, so information I'm going to need is, I'm going to solve for t. And so, we can call it, I'm going to call it t underscore c, since I know Antoine uses temperature in degrees C. And then, what else will I need? I'll need my Antoine constants for each component. So I'll use ant hex 1 and ant cyclohex 1. So ant hex 1 and ant cyclohex 1. Okay, ant cyclohex 1. Okay, and we'll pass these via an anonymous function in a second. Okay, so then the first thing I'm going to do is, okay, we can leave this up here as comments to, remind you of essentially what we're doing. Then the first thing I'm going to do is if I'm going to use F0, and F0 is going to essentially solve for the temperature in degrees C for us, right? It's going to iterate on T. Well, actually, do we want, well, C or Kelvin, it doesn't matter. So let's leave it as C, because that's what Antoine uses. Then what we just would need to make sure we do is if we collect temperatures in degrees C, the reference data is in Kelvin, so you need to convert the reference data to C, or you need to convert the reference data to C, or you need to convert the data we calculate to Kelvin, right? One or the other, okay? But anyways, so with my temperature in degrees C and my Antoine constants, first step would be let's compute P1 sat and P2 sat with guess value of TC, right? Where F0 is going to be what's guessing that value of temperature, okay? So how do we want to do that? We could have an Antoine calculator. Let's do that in the spirit of modulating our code. So let's do a function res is Antoine P, and Antoine P is going to take his inputs TC, and I'll just have ant. Okay, and so I'm going to start by unpacking my Antoine constants. Okay, and again, I'm trying to modulate and break everything up, because looking at this, I think you're right. You have the right idea, but my guess is it's just trying to do too much with an anonymous function, which is what's causing your issue. If this, presumably you sent it to me because it wasn't working in the first place. So I'm going to unpack. So let's just do A is ant1. Okay. So unpacking is something that's not necessary, but again, I like unpacking when I have vectors like this, because it allows me to write my final expression in a form that I'm more accustomed to. Okay, so log p. Okay, so my Antoine equation is just a minus b divided by t plus c. Do I not reproduce my Antoine equation? I don't have it here. We had it back in chapter 1. At this point, it's burned in my head. So it's a minus b divided by t plus c. Okay, I call this t underscore c to remind me it's temperature in degrees C. Okay, so then p, which is in units of millimeters of mercury, will be 10 raised to the log p. Okay, and then what I'm looking at is up here, you converted the pressure to kilopascals, or from kilopascals to pascals. But you know what? I'm going to keep it in kilopascals, because as long as we keep our vapor pressures and our pressure in consistent units. We can use whatever ones we want. Okay, so then I'm going to convert to kPa and return. So res would be P in millimeters of mercury times 1.01325 e to the 3, right? So 101.325 divided by 760. Okay, I believe. I believe, right? Because it's 1.01325 times 10 to the 5 pascals. So 101.325 kilopascals. Okay, so let me return my vapor pressure. Bam. Okay, so bam. So let's compute with guess value of Tc in kilopascals. So I'm going to compute those vapor pressures in kilopascals, and I just remember from doing this, that's my Antoine expression, and it uses temperature in degrees C. So P1 sat, okay, would be given by Antoine P, Tc, Ant hex 1, P2 sat, it's going to be Antoine P, T underscore C, comma, Ant cyclo hex 1. Okay, bam. Okay, and now I look at my mole balance design equation. So I have P1 sat and P2 sat. Okay, I'll need to pass X1, right? So I'm going to be looping over X1. Okay, so X1 is going to be I'll need to add to my input list. Okay, so for convenience, define X2. Okay, so X2 is equal to 1 minus X1. Again, it's just going to allow me then to write my air function in this way. And so as I write my air function, I'm going to also need my pressure in kilopascals. Okay, and so as long as I'm consistent with my value up here, I'm good. Okay, I want to make this a lowercase p because I like to use lowercase for scalars. Okay, so I have pkPa, and so then my air function will just be res is p in kilopascals minus, and I'll do x1 times p1 sat plus x2 times p2 sat. Cool. Bam. Okay, and if you want the fancy word for it, this is what's called a bubble P calculation. Okay, cool. All right, so what I'm going to do now is, okay, let me go up here and peek. So we can keep all that the same. Okay, these are a lot of x values. Okay, I'm going to use length space to go from 0 to 1, and I'm just going to go for 100 data points. If you want to, beef it up once you make sure once it's working, you could, add a third argument that's as big as you want. But I'm going to keep it at 100 for now. So we'll create our vector of t's. Okay, so that'll be, and I'll call it, t underscore c. Remind me it's in Celsius. Vector of y values, and then here's our vector of x values. We're going to loop over, and sure, we can keep that as our initial guess. We're in degree C, so it should be okay. Okay, so I'm going to loop over x, and so update my comments, my TC and y1 vectors. Okay, so now I'm going to need to reduce, so I'm going to call this, T air. Okay, my air function for T. Okay, it's going to have as its one input TC, my temperature in degree C I'm trying to solve for. Okay, I'm going to delete this. Bam. Okay, so T air is going to have as an input TC, temperature in degree C, temperature I'm trying to solve for. And what I'm going to do when I pass that, or for that value of tc that I passed to my reduced error function, I'm going to call result error with that value of tc, then and hex1 and cycle hex1. Now x1, right, would be my x1I, right, my x for that given loop iteration, and then p kilopascals would be my pressure up there. Okay, cool. So then the ith element of my tc vector would be f0. Now I call this t error, and I can use an initial guess of t naught. Okay, fine. All right. Now then, the question is, okay, once I solve for t, how do I go about solving for y? Okay. So, I add the two of them together. That gives me this error function, which I've eliminated y, that allows me to solve for t. So if I want to solve for y, okay, I can go to either one of these expressions and just, y1 would be x1 times p1 sat divided by p. Okay, so, we could do this. So y1 of I, okay, oh, and actually now it's good that I created this Antoine function, would be x1, right, my ith element of x1, times, well, p1 sat would just be Antoine p, that's what I call it, right? Antoine p, okay, and it's going to want the temperature I just computed, we'll call TCI, right, my ith temperature, which I just computed, and so if we just play with p1 sat, so then that's and hex1, so that gives me p1 sat, and then I divide by p underscore kPa. Okay, and that should be it. And then if I want to confirm it's working, let's create a plot. So we'll do a hold on, and let me plot x1 comma t underscore c. So this is temperature versus x1. Okay, and we can plot that as, say, a red line. Okay, I'm going to plot y1 versus temperature as well. Let's plot that as a black line. Okay, save it. All right, you can add our labels and whatnot. Again, remember my temperature here is in degrees C that I just solved for, assuming this works. The reference data that you're asked to compare to would be, is in Kelvin. And so if you're comparing that reference data, make sure you convert the reference data to C or convert this data to Kelvin, your choice. So then let's just call Gabe. Okay, res is just underlined because I don't actually save anything to res and store it as an output. So undefined function of variable x1. Oh, so since I called that big x1, when I size them, that needs to be a big x1. Okay, hey, it works. Okay, yeah, it works. So there's my TXY phase diagram. Again, in the problem statement, you need to type up all the reference data and add that to your plot. Again, remember this is temperature in Kelvin. I've just plotted in degrees C, so you just need to convert them so that they're the same. And then it also suggests you make a McKay-Thiele diagram, which is just plotting y versus x. Right, so adding another plot in which is just y versus x, and adding to it, y equals x line. But yeah, hopefully that should be straightforward. So hopefully that helps you out and gets you set up.